all waiting for one.
Okay, folks. Number one, when you're not using the markers, make sure the lid is on super, super tight. Otherwise, they dry out super quick. And if you find a marker that's bad, don't put it back. Please throw it away. So we will end today by making a list of exactly what AP multiple choice you should be looking at and which ones we're going to quote skip. But because we have, I'll say, fewer ones to go, and these are a little bit more straightforward, I thought it would be good for us to kind of practice a little bit on our own. So you're going to be working on your whiteboard. When you're done, you might choose to take a picture of it, or you might choose to copy it on lined paper or on your AP multiple choice. And if you find the whiteboard is slowing you down or annoying or it's not working for you, you can obviously give up on the whiteboard if that's the case. So, all right, today I want to focus on going over 20 through 41, but in third hour here, we actually did a lot of the Kepler's Law ones already, so we're a little bit ahead of where I will be fourth hour. But I'm going to start at number 20. So I'm going to be working on my paper the same way that you're working on your paper, but I'm going to let you get ahead of me, okay? Because I want you to start to think about it. Now realize you have a little benefit in that I've already kind of sorted the questions, and you can notice that these questions start under the word V-orb, orbital velocity. All right, number 20, the radius of the Earth is approximately 6,000 kilometers. The acceleration of an astronaut in a perfectly circular orbit 30 kilometers above the Earth would be most nearly. Most nearly means like kind of like rounded off in case somebody uses 10 and somebody else uses 9.8 or something like that. The acceleration of somebody in a circle. Do you remember what the equation for the acceleration of somebody in a circle is? Pardon?
GM over R squared.
GM over R squared. That's the velocity of somebody in a circle. What's the acceleration for somebody in a circle? People always forget this equation. I'll give you a hint. Look in the back window, second window, purple equations. The acceleration for something in a circle. What is the, let me say it again. It says the acceleration in a circular orbit. Do you see the V squared over R? Do you realize that this is an equation? A equals V squared over R. That's truly an equation. That's the acceleration for something in a circle. All right, so maybe you could use that, maybe, and see what you can come up with. Scribble on your whiteboard, see what you can kind of work out. I don't know, see what you got.
What's the maximum window? That's what I thought. When you solve for the
who said the GM over R thingy? Who said that? You did.
Yeah. So I thought you find the mass and then you just plug that in to get the V orb.
Okay, so I'm talking to myself. Let me show you what I'm thinking.
Yeah, it was like
Okay, this is what my mind was thinking. I'll be honest. I don't know if I'm right or wrong yet. I'll figure it out here in a second. I was looking at this. V squared over R is the acceleration in a circle. So I was going to take V orb and figure out what that is, and then square it and divide by R. Is that what you did? All right, that's what I'm going to try. That's what I'm going to try.
Oh, wait, hold on. No.
And the radius, I think we have to add on the 300 above. So we have to add on the radius of the Earth plus that 300 kilometers. So I'm going to change that into meters. 1, 2, 3. So the R is going to be RE plus 300,000. And they want me to use the radius of 6,000. So divided by.
That's just.
1, 2, 3. 1, 2, 3.
Oh, oh, wait, hold on.
Divided by
Yeah, I got 10.96.
6,000. 1, 2, 3.
I got you.
1, 2, 3.
Oh, hold on.
I don't know if I was really good at that.
Yeah, I know.
But you will by the end of the year.
Yeah.
All right. Mine worked. I feel good about mine. Okay, so I did the orb GM, and I used the mass of the Earth divided by R, but this was my R. And then I squared that and divided by the same R again and got roughly 10. All right, we all okay with that? That was the, yes, that was the other thing that I thought of after I said this to you. And so, because what William said, I think what you quoted me, William, was you said the acceleration GM, and I think you said over R, but maybe I misheard you. R squared, yeah. And so that is the acceleration due to gravity at a location. And because we're on a perfectly circular path, that works too. That works too. Okay, so either one of those. Okay, so we figured that one out. That's good. That's good. Okay, would you read number 21 and try number 21? 21. Acceleration. I think we could kind of do the same thing that we were doing before. Like we have discovered that the centripetal acceleration equation works, and because they're in circular paths, this acceleration works. I think I'm going to stick with what William said. I'm going to try that one. And again, I'm just trying it. I don't know how to do it either. I'm just trying it. If R2 equals 2R1. All right, I'm just going to figure out what A1 would be. A1 would be G M over R1 squared. A2, what do we know about A2? A2 is G M and R2 is 2R1. 2 R1 squared. So A2, so this side becomes 1/4. How do I get the R1 in there? How do I get the R1 or the A1? A2 is R2 is 2 times R1. Did I write that right? I think so. The accelerations are related by A2 is 1/4. Do you know what? I can see the 1/4. I just don't know how to make it like work out mathematically that it's A1. Does that make sense? I'm just, pardon? Yeah, I'm just gonna say like this is A1. And A2 turns out to be 1/4 of that. I see that.
No, A2's bigger, right?
A2 is
Bigger, so you put that 4
4.
on top.
1/4. Yeah, but hold on. But why am I taking the 4 to the top?
So like 1/4 A2 equals 1 A1.
Yeah.
Tell me what to write. 4
Is it the number?
4A2 equals 1A1.
And then just define A1, it's just like 2. So you divide the 4 and then
Gotcha. Okay, so they're saying A2. I don't know why that didn't click to me. All right, thank God you guys are here today.
What I'm confused about, what about the A equals B squared over R equation?
Well,
And because it doesn't say acceleration due to
no,
gravity.
it's not. It's really, in fact, it's not even asking me to find the acceleration. It's asking me to find the relationship between the accelerations A1 or A2 and A1 are related by. Do you know what I mean? They're really just looking for how they relate to one another. Okay.
But wait,
All right, let's just keep rolling, okay? Because we got a lot to do. Do you know what? Do you see the kinds of games though that we're playing? Okay, we're looking
it says
for.
acceleration. And this one says acceleration. Does the same acceleration be gravity?
No, this one doesn't. This one says the acceleration.
Number 21.
I know, but I'm going back. This one says the acceleration would be most nearly. The acceleration would be equal to. So this is we're solving it.
Yeah.
This one we're just making a relationship by the two. And so I'm just making a relationship of the accelerations.
Yeah, but what I was thinking is that like when you use the A over B squared over R, then you get like two completely different. You get like a completely different answer.
All right, we're gonna come back to it. Okay, move on to 22. Okay, move on to 22. I'm gonna circle 21 and I'm gonna play with that at the end of the hour or during my lunch. All right, this time they threw a V in the story, so I think they're kind of pushing us to the V orb equation. satellite to move, for the satellite to move in a stable orbit, 2r. So I'm going to put a 2 in there. This side.
But you're trying to show, it's like a comparison, like every time it's a comparison. It's like a one.
And I did it this way. I wrote down the equation. I said, okay, we're going to make this a 2r. And then it means that this side becomes square root of 1 over 2 bigger. So then this side, which used to be v naught, is now square root of 1 over 2 bigger. Square root of 1 is 1. This is square root of 2. And so I think that's where they're getting their answer from. This one makes more sense to me than the one before. Okay, that one makes more sense to me. Okay, let's try 23. I thought 23 was kind of tricky.
No, we decided not to do that. It's a very similar.
Jacob, Michael, 23. We're rolling. Satellite X. All right, I'm talking to myself. Satellite X, we have two satellites, an X and a Y, so I'm going to sort them out. X has the radius r. Satellite Y is also in a circle, and it completes one orbit for every 8 orbits done by X. So that means it's taking Y longer. He makes one time around, one orbit, while this guy's making 8 orbits. So I call this T. So I'm going to call his 8T. He takes longer. I think that's right. What is the orbital radius for Y? Yeah.
It says that satellite Y completes one orbit for every 8 by X. So isn't it supposed to be 8?
I played with this, but I have done this problem like flip-flopped many times, but this is what I figured out. When this guy makes one orbit for 8 of these, so picture X. He's going around 8 times while Y makes one circle. So his T has to be longer. Does that make sense? So T is a unit of time. Yeah, T is a unit of time. So, and you know what, Kayla? I realize it's subject to, when I say interpretation, I mean it's confusing, but watch what happens when I do this. All right, I'm picking this equation because this equation is for things in a circle, and it's got T's and R's in it. And so for X, This could be the equation for x because it has a t and an r, and that is the relationship with t and r. Now let's make it look at y. So for y, this is an 8t. So this side becomes 64 times bigger. So this side has to still be equal to it. So what would r have to be in order to get a 64? If this was a 4, then that would work. And so Kayla, when I first did the problem, I switched them because I interpreted it that way, and then there wasn't an answer. Okay, so yeah.
I did like, you know, you do the proportion
Yep.
thing. Is that okay if I did it like that?
Yes, because really, what am I doing with this? Nothing, right?
Yeah.
Yes.
Okay.
Yep.
Hmm.
So I'm not saying that all of the questions on the AP exam are like these relationship kind of questions, but I am saying there's a lot of them for gravitation. There's a lot of them for gravitation. Okay, so 23, you can cross off 24 and 25. To be honest, they're great questions, and I hate to cross them off. But the reason I'm crossing them off is they have these Greek letters in them, which is the next unit that we're learning. So we really don't know those Greek letters yet. So we really can't do 24 and 25 right now. That is now pushing us to number 26. 26. I'll let you read it. All right, 26 wants me to find kinetic energy. Just 1/2 mv squared. The satellite is mass m, and it's in a circular orbit, so I'm just going to plug in v orb, and then I'm going to square it. So I'm going to make this v orb, and when I square it, I'll get gm over r. Why don't I have the answer circled? So a gmm over 2r, what one is that? B? I think that's B. That's what I think. Okay, number 27. Read the question, look at the picture, and make sure you agree with the answer. So I have to look very carefully. The short burst happens at point P. The arrow's pointing this way, which means he's like projectile motioning that way. So here he goes, projectile motion, but it's too fast. And so we get the egg going on that way. If it was perfect, I'd hit the circle. If it was too slow, I'd crash into the earth. And if it's too big, I could escape forever and be gone. If it's way, way, way big. Okay, escape velocity, 28. We are now moving on to escape velocity equations. 28. We escape. this is VE. VE. Would be the escape speed from a surface with twice the mass. Twice the mass. Let's put in a 2. And the same radius. So this side is getting square root of 2 times bigger. So this side, which was called the escape, is getting square root of 2 times bigger. So that one's pretty straightforward. You okay with that one? Okay.
Yeah. No.
All right, 29. I'll let you read it. Planet X has half the radius. I'm going to write 1 over 2. An astronaut weighs twice as much on planet X. But there's no small m. If the escape velocity is VE, then the escape velocity is. He weighs twice as much. Do you know what? That's making me think of this equation. Fg equals GMM over R squared. So if he weighs twice as much, if this is a 2, like he weighs twice as much, what do we know about the radius? That would be a half. I'm thinking. The radius is half. The astronaut weighs twice as much. I'm not seeing this one yet, guys. If the escape velocity. There's got to be a secret in here. The astronaut weighing twice as much because he's not over here. All right, this is my, I'm not, kind of like have it in my head, but I'm not sure I can say it. So if we know the radius is 1/2, so I know this down here is going to become a 1/4, which means that 4 is going to bop to the top. And if this is a 4, it tells me that the planet has to be a 1/2 because I have to have a 4 over 2. I have to have a 4 over 2 to get that 2. So if the planet is a 1/2, and I put a 1/2 over here for the planet, 1/2, then it doesn't change. I think that's it. You want me to say it again?
Yeah.
Let me try to say it again. And I'll be honest, I'm not sure I would have figured this out if the answer wasn't in front of me. Like for me to have to like work to try to get it, which isn't fair. But all right, let's store that. Let's store that for a second. So we know this is a 1/2, right? Because it told me the radius is 1/2. All right. But there's a reason he told me what he weighs. So this is the equation. Colin and Sydney, just hang on a sec. This is the equation for what somebody weighs. So I have to play with this equation. So I'm just now talking to myself because it says that somebody weighs twice as much on planet X. We don't know the mass of planet X, but he weighs twice as much, which tells me it's probably a heavy planet. So I'm going to make this a 2 because he weighs twice as much. But I know the radius is a half. And when I square that half, that becomes a 4th, which means the 4 has to bop to the top. 1/4, the 4 goes to the top, so I can cross that out now. This is not equaling. So that tells me I can't change G because it's a constant. The astronaut's mass is a constant. It tells me that the mass of planet X has to be 1/2. I'm going to put in the 1/2 in a different color. 1/2. How do I know it's got to be a half? Because I need a 4 divided by 2 to get a 2. So the mass of planet X has to be a half. So now when I come over here and say, oh, and the mass of this planet is 1/2, then this 2 cancels with the 2, and then that wouldn't change. That's tricky. I think that's tricky. But I think that's the way we need to approach that one. Okay, let's see if we can end on a better one. Yeah, I think you guys can chunk out 30. 30 is a cool one. I like 30. It'll bring our confidence back. Okay. What is the ratio? Just do the ratio. VE over VO. What is VE? 2GM over R over GM over R. Are we going to multiply by the reciprocal? R over GM. Cancel, 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 cancel. And I think we get a big fat square root of 2 left. Right there. That's a good one. I like that one. I like that one. Okay, I know we already talked about these, but we're going to hit a couple of them again so I can highlight them for today very quickly. We do not have to worry about anything that has the word angular momentum in it. So I'm going to cross that out. Number 32, the answer is that the angular momentum remains constant. Angular momentum always remains constant, but we're going to cross off that one. We already did 33, which I think was an RV equals RV. So I'm just going to write that in there. We're going to have to cross off 34 because it's got the W, again, the Greek letter. And I think we already did 35, which was an RV equals an RV. Correct me, Ron. Can we do that one?
I think it was you give it to us.
Oh, okay. All right, then let's pause. Let's do 35. Let's do 35.
Oh, it's yours.
We're doing 35. Oh, and by the way, how did I know it was an RV? Because I saw the elliptical path. And I saw velocities and radius, so that was kind of like my clue. Distance, so we're looking for I think we're solving for our B. That would be this.
It's just being
Yeah.
I get RA over 5. RA over 5. Okay, moving on. I crossed out 60 or 36 because it has angular momentum in it, so we'll skip that one.
Wait, hold on. Let's look at that back.
For 35,
Yeah. That's the
35. 36, we did 37.
We
We didn't do 37?
and I was stuck on that.
Okay, so let's look at 37. 37. I thought we did all of these, but I guess not. Okay, 37. All right, so when I look at the picture, should I be using RV?
No.
No, it's a circle, so I'm going to be thinking of V orb, right? I'm going to be thinking of V orb. All right, 2 satellites, travel satellite opposite directions, V1. The orbital radii, the ratio of the speeds. So this is like V orb of 1 divided by V orb of 2. So I'm just going to plug in my stuff. So V orb of 1 would be G M over R1. The orb of 2 would be G M over R2. So I just have like a fraction with a fraction in the denominator, which means I'm going to multiply by the reciprocal. So I'm going to flip it, and I'm going to have an R2 over a GM, and that's going to be gone then. And I'm just going to multiply these. I got a square root of GM on top. I got a square root of GM on bottom. So I think I get a square root of R2 on top and a square root of R1 on the bottom. Is that a choice? Yeah, A. All right, I'm crossing out 38 because it has the word angular momentum in it. Did we do 39? Let's do 39.
No, really tall.
Gentlemen, you're distracting me. And the video that people are listening to. Okay, so U1 is the potential energy of a planet satellite system. Let me draw that. Planet. Here's a planet. I should have called it an M, like the mass of the planet. Here's a satellite, lower M. So when I say system, this whole thing has potential energy, U1. And now I have another. U2 is the potential energy of a planet satellite system containing a satellite of mass M2. So I have another one. M with an M2. Going around. This is the potential energy of that. Which of the following expressions best represents the ratio U1 divided by U2? So I'm just going to do that. U1 divided by U2. The potential energy is G M M over R. Negative. That would be like R. This would be like mass 1, radius 1, because he's from system 1. This guy is going to be G M because it's the same planet. M2 R2. We're doing the same thing. Flip it upside down. Negative R2 G M M2. Cancel the negatives, cancel the G's, cancel the planet. What's left? An M1 R2 and an R1 M2. Looks like they just like flipped them around a little bit there. Flipped them. Okay, I know we talked about 40 and I think we talked about 41, correct?
Yeah.
Okay, so I want to make sure that we all have the same list now. So if I make this list, I'm going to make a list of what we talked about. And I don't know if you want to write it in the way that I wrote it here, but I'll share it this way. We said that problem 1 and 2 dealt with the force of attraction. And I picked problem 1. So in that sense, you could ignore problem 2. I said that acceleration due to gravity 4 through 8 were good examples, but we picked number 4 and number 8. So you could write those down. I also liked 9 and 10 as a collection. I told you that I also liked that number 1, problem number 1 on homework 1. It's kind of like I can take those same pictures and turn them into kind of like a multiple choice question. We need to do something with those graphs. So I might pick a question like 3, 11, or 12, like one of those. But I may also go back to notes 3 and just like ask a different question that's not AP level or AP style, just to make sure we know our graphs. There was the conservation of energy one that was in variables that we did the other day that I thought was a really good question for us to spend some time reviewing. I think it was number 13. It was number 13. So I'm going to mega circle number 13. All right. 14 and 15 are very similar. They're almost like the identical things. So I'll pick one from probably that collection. Sometimes people forget what is the gravitational potential energy of a system. You know, we actually just did it right here on number 39. People forget that. You can find the potential energy of a system by having a big mass and a little mass, and that this is the potential energy of the system. So this is not a hard question. But if I gave you a planet in a mass and literally just ask you what is the gravitational potential energy, again, not AP level, but knowing that, and obviously the negative. Those calc relationships, all right? So I circled 17 and 18. I crossed off 16 and 19. So make sure that you have that. All right, you and I just did 3 more sets today. Let's clean up the sets here, okay? So we did V orb, and we started at number 20, 20, 21, 22. All right, I'm going to circle 22. And then I'm jumping to 26. I'm going to circle 26 and 27. I'm circling 28 and moving to the escape. 28. And I'm circling 30. I'm moving to Kepler's laws. 33. I'm going to circle 35, but 33 and 35, I'll hook them together. They're identical. 37. All right, I'm circling 37, 39. Those are pretty basic. You can do that. And I'm going to circle 40 and 41. So I will only pick questions off AP that are on the circled ones. And honestly, those are what I feel like are the straightforward, doable ones. But I'm going to have maybe a few questions that are not AP level that are just make sure you know your stuff. No Kepler's first law, no Kepler's second law, Kepler's third law, et cetera, et cetera. So I will circle those right there. Kepler's 1, 2, and 3.
So just you said all of those plus Kepler's.
Yeah. Like just be able to like identify which one is which. Okay.
Yeah, I was like, the one that we were doing, the 21, I was
Yeah.
like, if that one was on the test.
Yeah, no,
I
you know
was
what? And those are, when I say that you can get a 4 by getting a 50%, the ones that I didn't circle are the ones that we might get wrong.
Yeah.
Okay.
If that one's on the quiz, I don't know. how many
That's okay. So I hope when you go through here, you find out that the ones that we circled are pretty straightforward. Okay.
Thank you.
All right. Have a good day tomorrow.